honored to be here because, you know, I got an invitation to come here. It was over 2 years ago, just before the pandemic started up, and I said yes, and I had planned to come, and then we had to cancel, or first of all, we postponed, and then we canceled. So it's great to be here finally after 2 years. And I think that's probably one reason we have a good turnout today is because people are homebound all these months and years, are really anxious to get back into things like this. So thank you for coming. I hope I can live up to your expectations. So I'm going to show you a slideshow of mostly still photos. I do have a lot of video. I have a drone that I've been using for years, many years now, and I do have a lot of drone footage, live drone, you know, real life drone flying around at low elevations, up close and personal to these ice age floods. I'm not going to show you any videos tonight, but if you want to see videos of these same features tonight, you can go to my YouTube channel that the gentleman introduced me to earlier. On YouTube, Ice Age Floodscapes, you can actually see a lot more up close personal information on there. Tonight I'm just going to do a short synopsis of what I've been studying for 40 years, almost 50 years now. I first started, when I was a graduate student at Eastern Washington up in Cheney, I chose a thesis to work on the Tushy beds, which if you haven't heard of, if you're local, you've probably heard of the Tushy beds. And I studied in Burlingame Canyon and a few other places not too far from here. So I actually started on my floods work here in the Walla Walla Basin. And so I have a special connection with Walla Walla, and I love this area. And I love living here, and that's why I retired here. So anyway, here's a picture of Dry Falls. How many people have been to Dry Falls there? Probably most of you have. If you've been there, you've probably driven in off the highway into the visitor center, which is this white little dot right here is the visitor center in the parking lot. And from there, you can look into the Dry Falls, and it's an impressive view from there. But when you're in the falls, all you can really see is this first part of the horseshoe here. And there's another whole horseshoe or a cataract cliff, as we call it, a cataract canyon. There's two of them here. And when the floods came down from Grand Coulee from the north, they came down and they dropped 400 feet over this cliff down into the valley below before they continued on to Soap Lake. But another thing you can't see is that this cataract complex goes for 4 miles. It goes another 2 or 3 miles to the west or to the east over here. There's another set or several sets of cataract cliffs where there was floodwaters moving all across that surface at the same time, 4.5 miles wide. And this is just one cataract complex that was being used. Maybe I should hold that. I should hold this so it's more steady. So this is one cataract complex that's 4.5 miles wide, but there's dozens of others that the Missoula floods, when they came down, when they hit the channeled scabland, they spread out for 100 miles. And this is just one of a few sets of cataracts that were carved by these floods. Okay.
Geology-wise, is that mud?
Geology-wise, one flood. The bedrock here is basalt, Columbia River basalt. That's pretty much all the rock in the channel scabland is all Columbia River basalt. It came out about 17 million years ago and ended about 6 million years ago.
Also, what's the orientation? Are we looking from the north to the south?
We're looking south. This is looking south. Soap Lake would be at the very top of this photo. Okay, let's see. There we go. Okay, so the Missoula floods were the main floods that we had in the Pacific Northwest, but there were two other sources of floods. One was Lake Bonneville down here. This is Missoula. Lake Missoula is up here in Montana, western Montana. We had at least one flood come down from Lake Bonneville about 18,000 years ago, and it went down into the Snake River and then came all the way through here. But that only happened once, and the evidence for that is, there's good evidence for that up here in Idaho, but we kind of lose the evidence when we get down into the Columbia Gorge. And then there's a third, smaller lake called Glacial Lake Columbia up here at the very end of the Ice Age. There was one flood that came down out of Lake Columbia when the ice sheet was retreating back north up into Canada. This yellow area was all glacier ice sheets coming down. And Lake Columbia drained when the ice sheet had advanced or retreated up into Canada, and that allowed one last flood to come down the Columbia River and then out to the ocean. So you can see the floods, all the floodwaters ended up in the Pacific, but they took different routes to get there. Here's another image showing you the topography of the Pacific Northwest. The white areas are the Pacific, or the Cordilleran ice sheet coming down from Canada. This is the Seattle's right here. Puget Lobe came down about as far as Olympia. There were no floods, big floods, like Missoula floods that came down out of the Puget Lobe. And then there's the Columbia Lobe that came down and blocked the Columbia River here at the upper Grand Coulee, created Lake Columbia that backed up behind the Columbia Lobe. And then there's a third lobe, the Pend Oreille Lobe that came down the Purcell Trench, blocked the Clark Fork River, and created this much bigger glacial Lake Missoula here. And what would happen is Lake Missoula would fill up behind that ice dam because the water had no place to go. It was blocked. The valley, the mountain valley where the rivers were draining through was blocked with ice. So the water was forced all to go down the one narrow canyon that destabilized the ice dam and caused it to fail. And then all that water from Lake Missoula would drain downstream towards Spokane into the Lake Columbia, which was already there. And it didn't take much more water from Lake Missoula to overfill Lake Columbia and then cause it to spill out across the Channel Scabland. Okay, and then from there it went down dozens of different coulee ways, Grand Coulee being one of the biggest, but there are lots of other coulees, anastomosing, branching coulees that are in the Channel Scabland in here. When the water got down to Wallula Gap, you know where that is, that's just west of here, a few miles. Here's the Walla Walla Basin, the Yakima Valley here. That water all converged onto Wallula Gap. Twice as much water was going in the gap could actually go through at once. So it was like turning on the spigot in a clogged bathtub where the drain's clogged. The water couldn't go through all at once, so it backed up and formed a huge lake called Lake Lewis in this area, and it flooded the Walla Walla Valley with hundreds of feet of floodwater here. So that's kind of the overall picture. Now we'll talk about more specifics. So there's the ice sheets coming down where the blue arrows show where the lakes form behind dams for the ice. And then those wet arrows offshore, during the Ice Age, there was so much water tied up in glaciers on land, it caused sea levels to drop 300 to 400 feet lower than where they are today. So this is where the modern coastline is here, but during the Ice Age, or Ice Ages, The coastline was way out here. It's 50 miles further west than where it is today. Now here's a more simplified version of what I've been showing you. Glacial Lake Missoula up here. This is filled a mountain valley, went up to 4,200 feet elevation, which in places the water was about 2,000 feet deep in Glacial Lake Missoula. There's the Purcell Trench lobe that was blocking Glacial Lake Missoula. And what would happen every few dozen years is the water would fill up behind the ice dam, and it would get so deep it would destabilize the ice dam, cause it to break apart. We don't know whether the water went underneath. It probably didn't go over the top, but it could have gone underneath, or just the pressure of the water pushing against the ice dam 2,000 feet deep was enough to fracture and destabilize the ice dam. We do know the water came out very quickly, just in a matter of 3 days or less. All that water from Lake Missoula drained out in 3 days or less. And that's about the size of a couple of the Great Lakes. Okay, so there's the ice dam. I need 3 hands. Okay, so there's what an image showing you where when the ice dam had failed and was removed by the water that was flowing behind it. It came down to Lake Columbia, overfilled Lake Columbia, and then spread out across the Channel Scabland. Spread out for 100 miles. It got down to the Wallula Gap. It's only 2 miles wide. So you can imagine why the water backed up so much. It backed up well into this area. We'll back up here a little bit. Okay, so there's a lot of flood features that are unique to the Ice Age floods. They're mainly at scale. There are features like this that occur in other areas too, but the scale, the size of these features is so huge that it's very unique to the Ice Age floods. And a lot of times when you're on the ground, you can't see the features for themselves because they're so big. You can't see the forest through the trees. So really the only way to get to see these things is up high. And that's why I have a drone and I've been flying, trying to get video of these features from the air. So they become much more clear and obvious. So the Ice Age floods were the brainchild of this man. Name was J. Harlan Bretz, who it was actually about 100 years ago, almost to the year, that J. Harlan Bretz was working here. And he was intrigued by some landforms he saw over here. He was a professor at University of Washington at the time, and he got a hold of some maps that showed some really unusual landforms. Like cataracts and coulees. And so when he was over in University of Washington, he would come over here on the weekends, and he started to become very intrigued by the geology of Eastern Washington. And he would drive around. He was a professor, so he would bring some students over with him. And he spent several years working here. And then finally in 1921 or 1923, he published his first paper proposing a huge flood of water, a giant flood. And his thesis at the time was the only genetic interpretation yet proposed, which is inherently harmonious and which fits all the known facts, is that of a great flood of water. Okay, and that was his outrageous hypothesis at the time. He didn't think it was outrageous. He thought it made perfect sense because he saw all the evidence for it. But all his co-workers, all the other geologists working with him, thought he was crazy. Here he was proposing something catastrophic. And they were entrenched in this idea that changes that take place on the Earth very slowly over a long period of time, and nothing happens very quickly. Grand Canyon is a good example of something that took millions of years to form from the Colorado River, eroding through it. And his co-workers thought that the floods had to have come, there must be another explanation besides something catastrophic. But it was, Brett's continued publishing papers and working in the field up until the 1960s and 70s. And it wasn't until the 1950s when other geologists and engineers and people started to get up in the air and they could see giant current ripples and other features like that, that they finally came around to Brett's idea of these outrageous catastrophic floods. So in 1979, when he was just shy of 100 years old, he was awarded the Penrose Medal, which is the highest honor you can earn as a geologist for his work on the Ice Age floods. And his only regret at the time was that he outlived all his critics. They were all gone, long gone, and he outlived them all.
What made him different than the other geologists to see that?
What made him different from the other geologists? Well, he was really stubborn, for one thing. That was obvious. Anybody else would have given up long before he did, defending his ideas. But he was very stubborn and opinionated, and he knew he was right. He had the evidence, and none of the other geologists that criticized him had ever come out to look at the evidence. And he published it, but that wasn't enough. You actually have to see it, up close to actually really appreciate it.
From a bird's eye view and just
Yeah,
walking
yeah.
the land.
Mm-hmm. Yeah, he had an uncanny ability. I don't think he ever went up in an airplane until the 1950s, which was long after his ideas had been accepted. But he was able to, in his mind, he was able to picture what was going on. So here's a good example. This is a satellite photo taken from space in 1972. This was taken. And you can clearly see the channels of the channel scabland, those dark lines running through this lighter foreground. The lighter foreground is wind-blown Palouse soil that accumulated on the surface over the last couple million years. And it overlies the Columbia River basalt, which lies underneath the Palouse soil. So the dark lines are places where the floods eroded the topsoil, the Palouse topsoil, down into the underlying basalt bedrock, which is dark and black. But in 1923, as early as 1923, Brett had already figured that out. This was a map he published in 1923. And on it, he went out and walked. He actually walked or drove his old car across the scabland, mapping where he could see channels. And he mapped where he saw flood deposits that were so big, boulders so big, no river could have transported them, or glacier. So he had all the evidence for these Ice Age floods early on, but it took other geologists decades to catch up to what he was doing.
So that Dodge was his field vehicle. He was walking across there rather than on a horseback.
He did lots of different forms of transportation. In most places we couldn't drive. 100 years ago, you couldn't drive across the scabland because there weren't any roads, or very few roads.
So
and the roads didn't go where he wanted to go, so a lot of times he was hiking with his students, or he took the train out from Chicago. So, some field seasons, he'd take the train out here from Chicago, and then borrow someone's vehicle. But most of the time, he had to walk through these areas. Okay, so here's another view of, closer up view of the Lake Missoula. This is the west end of Lake Missoula, near the Idaho-Montana border. The ice dam filled the Clark Fork River Valley with ice, so there was no place else for the water to go, so it backed up behind Lake Missoula. But then this is the ice dam, and this is the part that had to be broken up in order for that water to drain out. And when it did, when the ice was able to destabilize the dam, it flowed down into where Lake Pend is today, down into the Spokane area, across the Rathdrum Prairie. And then it encountered, during most of the Ice Age, it encountered another lake, which is at Lake Columbia, behind another ice dam. And all that water from Lake Missoula would spill out across the Channel Scablands.
So that's over how many years?
So how many years did the floods were active? The earliest floods from the last glacial cycle are about 18 to 19,000 years ago. And the very last flood was about 14,000. Yep. So that was the end of the Ice Age, 14,000. But that happened many times before. That happened most recently during that 18 to 14. But then there were other ice ages before that. Every 100,000 years for the last million years, there was another ice age similar to the one that the most recent. There's good evidence for that I won't go into here, but there is evidence for that. So if things keep going the way they are in about another 35,000 years, there might be another ice age here. Or with climate change, we may be pushing ourselves into an ice age sooner. It's hard to say. So this would be looking west, down the Clark Fork River towards, this is western Montana, and we're looking at near the Idaho-Montana border. So the ice dam here is in northern Idaho, and then we're looking west, and Washington would be way off in the distance here. So we're looking west. This is the lake, Glacial Lake Missoula, 2,000 feet deep, where the ice dam was. And there's the ice dam. When the water destabilized the dam, you can see it's a plug of ice that's filling the valley, so the water has no place to go. But with the ice dam broken apart, all that water behind the ice dam in Lake Missoula would rush out, carrying lots of icebergs. Obviously, right? Because there's a lot of ice that it had to break up, and when it broke up that ice dam, it carried those icebergs with it downstream. Is that better?
Pretty good photography back then. Yeah.
Pardon me? Oh, yeah, yeah. Yeah, this is actually taken by an airplane pilot, David Bennett, who hired another graphic artist to put in the ice dam and the lake. But all the topography, the mountains and things, those are real in this image. But
break up when the glaciers were receding, or was it still in an active advancing stage? So that ice
there's good evidence that it would happen both times. Sometimes as the ice was advancing, and as well as retreating. Most people in the past, people have always said it's because the ice dams were retreating, but there's evidence that they were forming. The floods would occur also as the ice was advancing. Yep.
Were there any fish in the ice water? Was it too cold?
Probably. I'm not a fisherman, but I know some biologists have worked on that. Sturgeon. And I should say that these floods were only 20 to 50 years apart after the ice dam failed, the ice dam is continuing to move. The ice behind it is still moving forward. It's like a conveyor belt. It's bringing down more ice, so the ice dam would reform. The lake would reform and refill. So 30 to 50 years after one flood, you'd have another one. They seem to be successively smaller. The earliest floods were the biggest, and the later ones were smaller. But still, they were draining. It was draining every 30 to 50 years. I don't know if that's enough time for the fish to get reestablished. It's possible that, and all the ice up in Canada, I mean, all the valleys in Canada were already full of ice, so they weren't migrating down from Canada. We know that. They could have been migrating in from rivers and streams that are downstream, but yeah, it's all conjecture. Okay, so how do we know that there was a lake there? What's the proof of the lake? Yeah, if you look at this, this is a picture taken just outside of Missoula, Montana, a place called Mount Jumbo. And you can actually, there's the freeway, there's I-90 right there. You can drive right by it on I-90. And you can really see these distinct shorelines. These are ancient shorelines for Glacial Lake Missoula. And they go up to 4,200 feet elevation, and then they stop. So that's how we know how deep the water got, 4,200 feet elevation. And you can trace that high water mark all the way around the perimeter of Lake Missoula. So it's not a coincidence. So this is a picture I took with the drone. Oops, wrong button. Okay, so there's the lake. It was up to 2,000 feet deep, I think 500 cubic miles of water, size a couple of the Great Lakes. And it all drained in just a matter of a few days.
Is that a volcanic throat?
Pardon me?
Is that possibly a volcanic throat of basalt?
This, no, that's,
The whole structure?
no, this is, Mount Jumbo is made up of rock that's 1.5 billion years old.
Oh.
It's much older than the basalt. They don't have basalt up at, the basalt only goes up to near the Idaho-Washington border, but it doesn't continue on into Idaho or Montana. So yeah, the rock here is very different.
So what is that rock, did you say? What is that made of?
Mount Jumbo?
Yeah.
Yeah.
Is it granite?
Oh no, it's a rock called argillite.
Oh.
Yeah, it's part of the belt supergroup. Anybody who's familiar with the geology, and it's 1.5 billion years old. It's an old continent that drifted into this area, billions of years ago, or hundreds of millions of years ago. So yeah, it's very old rock. And the interesting thing is we can see the rocks of Mount Jumbo, the argillite. We can trace it when the ice dam failed and carried icebergs with it. We can see that the same rock all the way down into the Willamette Valley of Oregon. And erratics, we can trace these erratics all the way down to out to the Pacific. But we see them in Oregon, all through the gorge, Tri-Cities area. They're all over. Okay, so here's another good example of evidence for flooding. This is a place called Camas Prairie. Has anybody here been to Camas Prairie or familiar with it? It's a pretty famous place for giant current ripples. Okay, so these ridges you can see these are ridges of gravel, mostly gravel, that were transported by floodwaters that were draining out of Lake Missoula. So when you unplug Lake Missoula, when you get rid of the ice dam, the water was all racing towards the Pacific. And when it did so, the lake was actually up here somewhere, up to near the tops of these peaks was the lake. But with it unplugged, the water dropped very quickly, and as it did so, it picked up speed as it was like racing through little passes like this. You can actually see that these ripples, they all point upstream into the direction of the spillover channel that's up here. So there's lots of good evidence for these huge currents of floodwater that were associated with the draining of Lake Missoula. Here's a little homestead here for scale. Okay, and then downstream, still in Montana, near Thompson Falls, there's a narrowing of the valley, the Clark Fork River. This is the Clark Fork River. It's forced to go through a narrow opening, a rock opening. This is all belt rock again, same as Mount Jumbo. And the ice never got up into this area. It was about 50 miles downstream was the ice dam. But this was all filled with Lake Missoula floodwater, or Lake Missoula water up to 4,200 feet. So the lake was up here. When the lake drained, suddenly all that water from Lake Missoula was forced to go through this one opening. So they can actually calculate the speed of the water. I think it was going 80 miles an hour, and how long it took for the volume of Lake Missoula to drain. And it's up to 3 days for all that water to drain out. And I just put a new YouTube channel, a new YouTube video on my channel on the Eddy Narrows, if anybody wants to see more closely. And the significance of this feature. This is a very significant feature for calculating the volume and speed of the floodwaters as they drained out of Lake Missoula. Okay, so this is looking at the lower end of the ice dam. We were looking at the upper end earlier near the Idaho-Montana border. But now this is the lower end. The lower end of the ice dam went all the way down to Lake Pend Oreille in northern Idaho. Okay, so this is the little town of, what's the name of that? Bayview. I think it's called Bayview, right? And this is Lake Pend Oreille. So these, you get two lobes here, fingers of water. These are lobes of ice that were coming down from the ice dam. And you see these arrows are pointing to common points in both pictures. So today you got this beautiful idyllic Lake Pend Oreille view, but back in the Ice Age, there was actually a big sheet of ice that was terminating there. Okay, that's the terminus for the ice, and the ice was still moving, but like I said, ice is like a conveyor belt. It's continuing to move forward. But here is where the rate of melting equaled the rate of advance. So the ice was basically just sitting here. It looked like it's stagnant, but it's not. It's sitting there because it's melting as fast as it's moving forward. Okay, so that's why these ice sheets only go to a certain extent and then they stop. So what we were just looking at is the south end of Lake Pend Oreille, which is this area here, and here's the ice dam that was coming down. And when the ice dam failed, all that water from Lake Missoula would come down to where the ice used to be, and it would burst out into Rathdrum Prairie. Okay, and Rathdrum Prairie is very flat. You won't find a river anywhere in Rathdrum Prairie. There's no drainage, no water streams or creeks draining through Rathdrum Prairie because it's all filled with these very coarse flood deposits. The water table is like 100 feet down. So any water or snow that melts in Rathdrum Prairie all just percolates into the ground. So there are no streams there. And then you got all these blue areas are lakes along the side of Rathdrum Prairie. And these are places where when the floods came through, they built up the floor of Rathdrum Prairie. Before the floods, Rathdrum Prairie was down here. Then after the floods, each flood would fill up the floor of Rathdrum Prairie higher and higher, and that ended up blocking the drainages of the tributaries coming in. So that's why we have these lakes surrounding Rathdrum Prairie.
So Bruce, the sediment from all those floods, was that a way to determine each flood? I mean, was there different?
And sometimes you can distinguish different floods based on the sediments, the stratigraphy. Sometimes you can do that, but when you're dealing with gravel, coarse gravel, when you have one gravel on top of another, it all looks the same. But if you had a period where the water slowed down temporarily or stopped, you might get a layer of sand or silt on top of that. And then if the next flood didn't destroy that, rip it away or erode it away, you might see evidence for 2 floods that way. And that's one way we determine the number of floods, like in the Walla Walla Basin here is a good example. So yeah, Walla Walla and the Burlingame Canyon, for example, is the Rosetta Stone for the numbers of floods that we see from Lake Missoula. We can count 40 floods in Burlingame Canyon. That was part of my thesis, is doing that study. And so that Walla Walla is really a great place to study the floods because there's evidence for separate floods. Whereas everywhere else up in the scabland, it's really hard to distinguish one flood from another. Okay, so now we're moving out onto the channel scabland. We've gone from where the ice dam was, where Lake Missoula was, gone down through the Rathdrum Prairie, and from there, from Rathdrum Prairie, the floodwaters headed for Spokane, and they went down. Spokane is up here, and as I said earlier, there was another lake already sitting in here, Lake Columbia, during much of Lake Missoula time, which didn't go away. It pretty much stayed there for most of the Ice Age. There was a big lake sitting in here. So the water from Lake Missoula would come down, it would hit Lake Columbia, and then it would spill out across what we call the channel scabland. And I like this figure because you can actually see the crop circles of agriculture that are actually active. And those are places that are still covered with this Palouse topsoil that wasn't all stripped away by the floods. That's why we have such good ag in the channel scabland. In between the flood channels, there's great ag. They're growing lots of wheat and other crops. But where the flood channels were eroding, you can see it stripped away all the topsoil. So that all you're seeing is the black Columbia River basalt underneath that was stripped away. Here's an aerial photo from near the Sprague area. Sprague Lake is actually, you can see Sprague Lake up here. So south of Sprague Lake, you get this butte and basin topography. That's a coin that was turned by Brits. Basins, isolated basins, buttes and channels, lots of Mima mounds. These little round mounds are called Mima mounds. They're controversial how they actually form, but
What you said again, what kind of mounds?
Mima mounds, M-I-M-A, Mima mounds are called. We know they had to have occurred since the last flood, because the flood would have wiped them out. You had water moving tens of miles an hour, maybe 50, 60 miles an hour across the surface. It was eroding into the basalt. There's no way the floods would have left behind these little mounds of silt, which is what Mima mounds are made of. So that's kind of a side topic, but this is typical of what the channel scabland looks like. It's all basalt, Columbia River basalt. In the upper reaches of the channel scabland, there's not a lot of relief except for these shallow channels. As we go further downstream, further to the south, the channels get deeper and deeper. They step down into older basalt flows and they carve deeper and deeper canyons as you go further south. Okay, so here's an example of the Palouse soil. The Palouse, we call it loess, L-O-E-S-S, is another term for this wind-blown soil that's really good for growing agriculture. And wheat growing especially is productive in this loess soil. But here you can see by near Palouse Falls, you can see 3 Palouse islands that were streamlined by the floodwaters. At one time, these islands were all connected with one blanket, one continuous blanket of loess. The floods came through, they eroded down in between the islands down into bedrock, basalt bedrock. Today is at the bottom of these areas between the islands. So these Palouse Islands, streamlined Palouse Islands, are typical of the channel scabland. And they are streamlined by the floods. The floods, in this case, they were moving from down here to the lower left. They were moving towards the Snake River, which is to the northeast up here. And in the process, they streamlined these hills. You can tell the flow, you can tell the direction of flow too by the orientation of these islands. They're streamlined like an airplane wing. They're always streamlined in the direction of flow for the floodwater. Okay, so here's another cataract canyon of dry falls. I had this on my cover slide, but this is looking from a different direction. Now this is looking kind of upstream towards the upper Grand Coulee. There's the visitor center over there. This is the cataract, 400-foot tall cataract wall. This is actually, Dry Falls has 2 cataracts, and actually there's a third right here that most people don't know about. When they think of Dry Falls, they think of 2 cataracts, but there's actually a third. And you can't really see it from the visitor center. But when the waters were coming over, they were probably moving 60, 70 miles an hour, and they dropped over this cataract, and when they did so, they undercut the basalt. The upper part of the lava up here was stronger, and the basalt at the bottom of the cliff is weaker, so the floods would actually excavate the weaker rock from the bottom of the cataract, and that until a point where the rock above it would collapse down, and that would maintain the vertical profile of these cataracts. This cataract started 50 miles downstream at Soap Lake, and with each flood, which we know there were many, each flood it would work its way further upstream. When and if there is another flood, that cataract will continue receding up to the north towards Steamboat Rock.
The land formation, how do you define cataract?
Cataract is the cliff, the wall of rock.
So is
That's
it cut out?
yeah,
Concave?
yep. It undercuts. The floods would actually undercut.
And that's a cataract.
Right.
So where did all that debris go that was cut away?
Where did all the rock go? Yeah. Do you know? Are you familiar with Ephrata Fan? It's down at the mouth of Grand Coulee, where it opens up into the Quincy Basin. There's a huge fan of basalt boulders as big as that wagon. They're spread out across it's spread out across the fan that's about 10, 20 miles wide, 10 miles long. It's huge, and it's hundreds of feet thick. So that's where all the basalt, when the floods were going down to Grand Coulee, they were moving fast because it was constrained. When they got out to the Quincy Basin, the flow spread out and it slowed way down, and that forced all that coarse basalt material to settle out of suspension. Yep.
That must have been some really fun detective work for geologists, to discover the sources of certain.
Well, we're still learning. We're still learning things all the time too. I mean, it's not the story isn't over. As we learn more, we have more questions. It's getting more refined, but there's still lots of information to be gained. Okay, so here's Palouse River Canyon. This is upstream of Palouse Falls okay? If you could see Palouse Falls, it would be down here in the lower left. But just above that, you can see where the floods, everything in this image, and you can see there's a railroad track down here for scale. Everything in this image would have been under hundreds of feet of flood water at the same time. During a flood, you wouldn't see any of this. All you'd see is water and icebergs floating around. So you can see the scale of the erosion that was going on.
So the erosion pattern's like threading right there. It's some diagonals going this way and
Yeah, they're. You can see there's a rectangular pattern, or it's not normal for a river to go straight, to carve a straight canyon. This is the reason they're linear. They're these linear features is because there's underlying tectonic fractures in the basalt, and they're more regional feature. It's not typical of all the scabland, but there are a few places in the scabland where we have these tectonic fractures that are developed as a result of stresses in the Earth's crust. And the floods took advantage of those. The rock is weaker in these linear fractures. The rock is weaker, so the floods actually took advantage of the weaker rock and those fractures, and preferentially eroded out the rock from those areas. The rock in between is stronger, so therefore it's not eroded as much. I'll probably get this at the very end, this microphone. Okay, so here's another feature called Devil's Canyon. It's about 10 or 15 miles west of Palouse Falls. Anybody here been to Devil's Canyon, know about it? Have you driven up the road that goes all the way up? It's pretty cool. It's near the town of Colotis, so if you go to Colotis and you head south towards the Snake River, it'll take you right down this canyon. Not many people know about it, and it's not really labeled anywhere. There's no sign anywhere saying, Devil's Canyon this way. But it is a spectacular feature. And again, it's straight and narrow because it was following one of these tectonic fractures. They're the same as the Palouse Falls area. Yep. Okay, so now the water is going across the scabland. A lot of it was coming down the Grand Coulee, coming from the north, which is up here. And when Soap Lake is just off this image here, but just at the mouth of Grand Coulee, there's this Ephrata fan. I haven't labeled it here, but this is Ephrata fan. This is the area where when all the rock was excavated, quarried out of Grand Coulee, most of it ended up down here at the mouth of Grand Coulee in this fan, the Ephrata fan we call it. But the water would continue south, and the lowest outlet for the Quincy Basin is down here at Drumheller Channels. But there's two other outlets to the west called Frenchman Coulee, Potholes Coulee. When the floodwaters were really deep and they couldn't all go through Drumheller Channels at once, that water would fill the Quincy Basin and rise up hundreds of feet to spill over a couple of these channels off to the west. Okay, so these are Potholes Coulee and Frenchman Coulee are much higher than Drumheller Channels, but the water was coming in so fast and furious that even the floodwaters that couldn't go through Drumheller Channels would find a way out to go through Frenchman Coulee and Potholes Coulee. These are a couple of really excellent places to go explore if you want to see flood features. They're both within state park land, open to the public, lots of trails and things in there. So I highly recommend these areas for exploring if you want to learn more about these features.
Great rock climbing there too.
It's a real popular rock climbing area at Frenchman Coulee called the Feathers. Those big huge columns, some of the biggest columns are in here. But there are some beautiful columns elsewhere. Even in Drumheller channels, there are some really good columns in there. And so the floods, some of the floods went down through Drumheller channels and then down, continued south through Othello channels. But other floods, they followed the blue arrows and went west to Potholes Coulee, Frenchman Coulee. Some of the water went down in front of along Crab Creek through here, and a lot of it ended up down here in the Basco Basin eventually before it was heading for Wallula Gap would be the next destination. How are we doing for time?
We got all
Okay.
night.
Got all night. You don't have any place to be tonight? Okay, so this is a drone picture I took of Potholes Coulee, ancient lakes. There's the Columbia River. You can see the reflection of it there. And this is an upland. This is a high Babcock Bench, Evergreen Ridge area that separates the west end of Quincy Lake from the Columbia River. But the floods were able to overtop this ridge line and then spill over to carve out these beautiful cataracts. Okay, so again, we have a dual cataract. There's 2 cataracts separated by a rock blade, a blade of rock, basalt, down the middle. This is a recurring theme in the Ice Age floods erosional features, is to see these dual and sometimes triple cataract canyons separated by blades of basalt down the middle. You won't see that in any other, you won't see the scale of this anywhere else except on the planet Mars. There is evidence from Mars that there were big floods that occurred, not tens of thousands of years ago, but I think it's 4 or 5 billion, very early in the history of Mars and the evolution of Mars. There was a lot of water at one time, and it created features very similar to this. But long ago, all the water disappeared, and there hasn't been any flood activity on Mars for a long time.
Can you get to these places by car?
By roads? Yeah.
Okay.
Yeah. Potholes Coulee, for example, there is a road you can take to get to about this point, to the lower end, and you can actually drive. I can't see the road here, but there is a road just off the picture that you can ride at the upper end too. And if you buy my book, On the Trail of the Ice Age Floods, I have directions on how to get there. Thank you for the plug.
Do you have one of those little planes that you just sit and then a bird comes by and sits on your shoe? Do you have one of those besides drones where you're actually up there?
No.
You should have that.
Yeah, that's a lot more expensive though, and
I see.
dangerous. When I'm flying a drone, I'm not endangering my life, like if I were taking an airplane or a small glider or something. So a drone, I like a drone because it's safe, and it's expensive to replace. But okay, so here's that other cataract canyon I was talking about, which is south. This is the other spillover point where floods spilled over into the Columbia River from the Quincy Basin. And it's a dual cataract canyon. This canyon, this is Frenchman Coulee, is longer than Echo Basin, which is a shorter cataract up here. In between, we have the Feathers. This is the popular area for rock climbers go, is right here.
It's a really good place to camp, and you can
Uh-huh.
climb up on top of that dry
Right. It doesn't cost anything. It's free. It's kind of free for now, anyway.
How deep is that? Is that little lake down in the bottom, is that leftover from the last
This
flow,
one.
or is it spring fed?
This lake here, that's irrigation water. Yeah, it's spillover. There are several excess irrigation water channels that feed into this lake, and then it drops over a waterfall right here into the coulee. Okay, people are starting to leave, so I suppose I should finish it up. So Drumheller Channels is another feature down there that I was talking about. This is a place where they have some of the best basalt columns anywhere are right along the edge of this island. This is a streamlined island that was streamlined by the floodwaters. Floods were coming from the north up here, and they were flowing south. And there's actually a streamlined island here that's pointing into the direction of flow for the floodwater. But this is a wildlife refuge. It's open to the public most of the year, and another great place to explore. Okay, I'm going to skip that. Okay, so I want to talk a little bit about Lake Lewis. This is the lake that formed when the floodwaters were converging onto Wallula Gap, which is right here. The waters rose up to about 1,200 feet elevation. And so that blue line, everything in blue would have been under 1,200 feet elevation. Everything in brown was above the level of the floods. So you can see all this water was trying to make its way into Wallula Gap all at once. When the flow came into Wallula Gap, twice as much water going in could actually go through. It reversed the flow of the Yakima River. So the floodwaters flowed up into the Yakima Basin. The floodwaters also flowed up into the Walla Walla Basin, which created the beautiful rhythmites that we have at Burlingame Canyon and other places. There's evidence for up to 50 to 60 of these floods during the last ice age.
What's the word called for the water dam that was formed up Gap? It's hydro something or, I can't remember.
Hydraulic dam? Yeah, it was, twice as much water going in. So hydraulically, it was a hydraulic dam. Yeah. It wasn't a physical dam, but it was, because of the physics. And there's a picture with a drone. You can see the scabland that was eroded. The floods went all the way up to the top, and they actually spilled over on both sides of the gap. The water spilled over and carved channels up high on the sides of the gap. You can see the scabland that was created here. There's two sisters. Okay, so what I mentioned earlier about lots of ice coming down with the floodwater, so there are lots of icebergs. The icebergs were loaded with rocks that were transported with the ice as it was eroding upstream. And here's some examples of erratics. Here's some floating icebergs within Lake Lewis. This is in the Tri-Cities area where I live. On Rattlesnake Mountain, we have a beautiful piece of argillite here that is that same belt rock that I was showing you earlier at Eddy Narrows. So it's likely this rock here came from Eddy Narrows, which was hundreds of miles away, floating in an iceberg. And this is a very big iceberg. Most of the erratics are granitic rock. 3/4 are granite or granodiorite, and the other 10 or 20% are mostly these argillites.
So where's the granite from? Where'd that come down from? The granite erratics?
Oh, sorry.
Where is the granite erratics? Can you place where they came from?
No, not as exactly. There's granite all over, all in the mountains. The Cascades have granite. There's granites up in northern Washington. The granite's all over, so we can't really pinpoint where the granites came from. Yeah, not yet. Someday they'll probably come up with a signature for differentiating, but that hasn't happened yet, and that would be expensive. Okay, so there are a couple other notable erratics. Okay, erratics again are these boulders that were brought in and floating in on icebergs. And one of them is the Bellevue erratic, which is right here in western the Willamette Valley. This is the Willamette Valley. During the Ice Age, the floodwater went up to 400 feet elevation, which is the blue. Everything in blue is up to 400 feet. And the areas other than blue were above the level of the floods. So the floods came down the Columbia Gorge. Some of the water, or most of the water, went this way towards the Pacific Ocean over here, but some of the water back flooded up down into Lake Allison and extended all the way down to the town of Eugene, Oregon. So the Bellevue erratic is over here, and then there's another erratic called, which is the Willamette meteorite, which occurs right here. And I'll show you those next. Here's the Bellevue. This is actually a state park. I think it's called Floating Rock State Park or something like that in the western Willamette Valley. This is from above, looking down, and you can see it's perched on top of a little hill here, a little knoll. And when you go down, get up close to it, it's one of these argillites. Again, this is belt rock coming from northern Idaho or Montana, maybe around Eddie Narrows. Same type of rock here. And then lastly, we have the Willamette meteorite, and which it's probably, if it's truly an erratic, there's still some question, there's still some debate about whether it is truly an erratic. The reason we think it is an erratic is because it's lying at the 400 feet elevation, which is the high water mark for the Missoula floods in the Willamette Valley. And it's occurring on the downstream side of a big island. So floodwaters coming in would have circulated, back eddied into that area, and there's been a back eddy going this way and another back eddy going this way. It's right where the two back eddies meet. You've got this meteorite. It's in there. The meteorite isn't actually there anymore. It was moved to a museum in New York, but you can still go see it. It's on display in New York City. But anyway, we have pictures like, this is one picture.
There's a model of it on the Eugene campus, so.
Yeah, there's replicas of it. Yeah, there's replicas, and they're usually not to scale. They're usually smaller than, because it's pretty huge. It's the 6th largest meteorite found in the U.S. Okay, so I'm going to finish up, just do a little shameless commerce here. This is free YouTube channel. Anybody can go to this online. I've done about 30 videos so far, mostly using the drone.
Is that your craft right there?
That's the one I had before the one I have now. I just bought a new one, better, newer and better. So feel free to go there. And then I've got 2 guidebooks that I've published. These are field guides for discovering the floods. A lot of the features, or practically all the features I've shown you today are in these guidebooks. And this is one I put out last year. This is my most recent one. It's a coffee table type book of mostly pictures taken with a drone and from fixed wing airplanes of flood features. So I think that's the last slide. Yeah. All right. Well, thank you for listening.
Q&A